Hello and welcome back. Today we are planning a mission to the moon. Well, it's only part of a mission, and I'm also using Kerbal Space Program, but the math should be the same. So, for anyone who isn't familiar with this game, Kerbal Space Program is essentially a space exploration simulator. It uses realistic physics to model orbits, and allows you to build rockets, planes, rovers, space stations, and whatever this is. It's probably one of the most realistic space games there is, except for the fact that all the planets are 1/10 scale. But some mods can fix that if you want to play in hardcore mode. So enough about the game, let's talk about the mission. I want to start with a spacecraft in orbit of Kerbin, the game's analog for Earth, and in an orbit of the Mun, the game's analog for the Moon. I'm staying in orbit because launch and landing make math much more complicated and end up using rule of thumb anyway. Our initial orbit will be circular with an altitude of 80 kilometers. This is a pretty standard altitude because it's close to the atmosphere, which ends at about 70 kilometers, but it has some extra room to maneuver. The final orbit around the Mun will be 11 kilometers because getting any closer would mean we can't speed up time by more than 10 times, which is just annoying. So we have our targets, which means we can calculate the delta V we need. The Greek letter delta stands for change, and v is velocity. So, delta v is a measure of how much we can change our velocity, which is super important for orbital maneuvering. If you want to know more about orbits, I've done a couple of videos that you might be interested in. The first step in this problem is to create our transfer orbit. Thankfully, this is super simple as the Mun is in a perfectly circular orbit with zero inclination, basically meaning it's perfectly in line with Kerbin's equator. What we need from this orbit is its semi-major axis, which is this distance on an ellipse, but in our case it's a circle, so it's just the radius. According to the KSP wiki, that's about 12,000 kilometers. We also need our initial radius, which is our altitude plus the radius of Kerbin. Again, looking at the wiki, we see that Kerbin has a radius of about 600 kilometers, bringing our initial radius to 680 kilometers. Now we need to know the maximum and minimum heights, also called apoapsis and periapsis, for our transfer orbit. If we add these together, we get the major axis, divide by 2, and we get the semi-major axis. And that comes out to about 6,340 kilometers. And the last thing we need to understand is the gravity of Kerbin and the Moon, which are summed up in something called the standard gravitational parameter. This is the mass of the body multiplied by the universal gravitational constant. For Kerbin, it's 3.5316 times 10 to the power of 12 meters cubed per second, and for the Moon, it's 6.5138398 times 10 to the power of 10 meters cubed per second squared. It's a weird unit. So we can finally start calculating our delta V for our first burn when we're leaving orbit of Kerbin and transferring up to the height of the Mun. So we'll start by finding our initial speed using this equation. So we plug in Kerbin's gravitational parameter, our initial radius of 680 kilometers, and the semi-major axis, which, because we're still in the circular orbit, is the same as the radius. By the way, you should make sure that you're using all kilometers or all meters for these calculations. I ended up using meters because it's easier to convert the heights than it is to convert the standard gravitational parameters. This tells us that our initial velocity is 2,278.9316 meters per second. Then, using the same equation, we can find our velocity after the burn by changing the semi-major axis to the new 6,340 kilometers, which we found earlier. This gives us a final velocity at periapsis of 3,135.2869 meters per second. Our delta V is simply the difference between these two numbers, and that comes out to 856.3553 meters per second. And with that, we're well on our way to the Moon. But we still need to find out how much delta V we need to slow down when we get there. First, let's find out our speed at the apoapsis of the transfer orbit using the same equation again. We keep the semi-major axis, change the radius, and it comes out to 177.6663 meters per second. Now we need to find something called V infinity, which is our speed when we enter the sphere of influence of the Mun. And quick crash course in Patched Conics, that is a tongue twister I didn't intend to write. But anyway, spacecraft feel gravity from the sun, planets, moons, and every other piece of matter at the same time. But it's impossible to calculate orbits including all of this. Yes, impossible, not just really hard. So we either simulate gravity or we have to use Patched Conics to calculate them by hand. Patched Conics assumes that there is always a primary source of gravity, but if you get too close to another object, it takes over. It's actually reasonably accurate if you use it carefully. The sphere of influence is the magical bubble around the moon where we start to feel its gravity instead of the gravity of Kerbin. And fun fact, this is actually how KSP simulates its gravity, unless you use a mod. Okay, back to the engineering. We find v-infinity by calculating the difference between our craft's velocity and the mun's velocity. Using our equation once again, we can find that the velocity of the moon is going to be 542.4942 meters per second. Also, because this is in the same direction as our velocity, we're going to subtract to find v-infinity, and it ends up being equal to 364.8279 meters per second. Now we pass into the sphere of influence of the Mun, but we find that our orbit is no longer an ellipse, it's a hyperbola. This is because we're going fast enough to escape the moon's sphere of influence again. So we're going to need a new equation to find velocities because we don't have a semi-major axis. You can derive this equation from several others, but to move things along, I'll just give you the equation. We plug in v-infinity, the gravitational parameter of the moon, and our target periapsis to find the velocity when we want to start braking. Remember to add the radius of the mun to the periapsis, so it's 211 kilometers, not 11 kilometers. That's a big difference, and definitely not a mistake that I made. Assuming I did all this correctly, our velocity at periapsis should be around 866.3284 meters per second. Now, to calculate the delta V for our braking burn, we use the old equation to find the velocity of our final circular orbit, which comes out to 555.6193 meters per second. We take the difference and we find that our second and final burn needs to be 310.7091 meters per second of delta V. This brings the total budget for our mission to 1167.0644 meters per second. But this is making a lot of assumptions, so just in case anything goes wrong, we should use a factor of safety. I'm trying to challenge myself, so I'm only going to be using a factor of 1.2. The official target is now an even 1400 meters per second of delta V, and it's time to actually engineer the spacecraft. Usually I just throw something together in the game through trial and error, but because we're over-engineering this thing, I'm going to do my best to minimize the weight on paper. In theory, cutting down on weight means we can buy a cheaper rocket to get our spacecraft into orbit in the first place. The weight of the fuel in the engine will end up being dependent on the weight of our payload, so we're going to start with all the command, control, and electronic stuff. The lightest probe in the game is the Probodobodyne Octo 2 at 0.04 metric tons, but it doesn't have any reaction wheels, meaning it can't point the spacecraft on its own. The lightest reaction wheel module is the small inline reaction wheel at 0.05 metric tons. Let's compare that combined mass of 0.09 metric tons to the lightest probe with built-in reaction wheels. It turns out there's a tie of several probes that all weigh 0.1 metric tons. So we're going with the Octo 2 and separate reaction wheels because it's slightly lighter. If we were considering the cost of the parts, this would be a different story because Octo 2 is actually pretty expensive, but I'm already putting way too much effort into this. Now that we can control the spacecraft, we need to give it power. Here, the lightest option is a single solar cell, coming in at 0.005 metric tons. It generates 0.35 electric charge per second, which is more than enough. Our probe core only requires 0.03 electric charge per second, and the reaction wheels take up to 0.25 electric charge per second. We have our payload, now it's time to optimize our propulsion, which is going to be a nightmare. Engines have ISP, which measures efficiency. Click on a card to learn more about that, but they also have different weights. So high ISP means less fuel weight, but a lighter engine means less engine weight, and we're gonna have to balance these two things. And just to make things worse, there's like 30 different types of fuel tanks we have to consider, and each of them is gonna have a different ratio of fuel mass to structure mass. Or so I thought. I actually made a spreadsheet to check this out and found that for rocket fuel tanks, there's two ratios, 8 and 7. The only tanks with the ratio of 7 are the Mark II, Mark III, or adapters, with the exception of ADTP-23 for some reason. So to optimize our weight, we can use any of the other tanks that have a ratio of 8 kilograms of fuel per kilogram of structure. I also checked liquid fuel, monoprop, and xenon tanks for their ratios. The liquid tanks are all over the place, but the best is the small Mark 0 tank with a ratio of 10. Monoprop also varies a lot, but tops out at 7.5 with the R1 tank. And finally, xenon has a pretty consistent ratio of 3. Now I can make a simple spreadsheet to find the best engine, and drumroll please, it's the Ant. I'm honestly surprised it wasn't the Ion engine. The Ion Engine is insanely efficient with 4,200 seconds of ISP, but the problem is the engine itself weighs 250 kilograms versus the Ant's 20 kilograms. In fact, the entire spacecraft built using the Ant should only weigh 195 kilograms, which is less than a single Ion engine. Fortunately, the Ant was my second guess because it's tied with the Spider for being the lightest engine in the game, but it beats it with a respectable ISP of 315 seconds. Because we don't need that much delta V, we don't need that much fuel, and the lightest engines end up being ideal. Just for fun, I tested to see what would happen if we increased our payload from 95 kilograms to 1,000, and I found that the Ion engine ended up taking over once its weight became less of an issue. The biggest downside to the Ion engine is that it has so little thrust, and this ends up making your burns take forever, which is 1, annoying, but 2, makes the math really hard because all the math we've done assumed instant acceleration, and the maneuver nodes in KSP do the same thing. So the longer it takes to do your burn, the less accurate your prediction is going to be. But anyway, let's go build this spacecraft and see how bad I am at math. Okay, so I was about to say hello and welcome back, but this is probably the middle of the video. I just finished the rough draft for my script of the moon mission video. All the math is done, so I figured I might as well build the rocket now and see if my numbers are sort of correct or completely off, and I was going to get my live reaction for it. So this is the probe core he picked, the Octo 2. The lightest yet extremely expensive one. I'm cautiously optimistic about my numbers. I looked at a delta V map, which is essentially a lookup chart of all the delta V's required to get to different places, and the burn to get to the moon is similar to what I found, even though there's slightly different heights in the orbits. So that gives me some confidence that I didn't completely botch this. You should probably start with the lightest tank. I think this is lightest. Oh yeah, 240, that's more than enough. Okay, so I'm looking here at the very bottom corner at our delta V. We're getting 1200, or I guess almost 1300. With our factor of safety, it was 1400. Without the factor of safety, it was 1167, I think is what I've written down. So that means this is technically enough, even though it's below our factor of safety. And I'm sort of tempted to try and do that. Oh, the mass is spot on too. 195. So it has slightly less delta V than we wanted because there's too much structure, but the mass is correct and it should be able to get us there. We'll see if I eat my words in a second. Alright, so we're gonna legitimately send this to orbit for the first time, I swear. Completely ignore that and the fact that the altitude's wrong. So first things first, we need to get this solar panel in the right direction. There we go. Okay, we are regaining power. So now we have to create a maneuver node for timing, not actually overriding our calculations. And periaps is at 2,000 meters. I think that's a timing issue though. Okay, so we're going to go ahead and warp closer to that node. Now, as a rule of thumb, you want to split your burn. We have a burn time down here of 1 minute and 12 seconds. You want to do half of that before the node and half after. In a perfect world, it would be like a 1 second node and you would do it instantly. That's not really an option for us though, so we're gonna have to split it by, 36 seconds, I guess? There we go. And you can see our little ant engine is taken away. We're gonna cut thrust early so I can change my thrust limiter so we can fine-tune this orbit. So now even at full thrust, we're very slowly changing the orbit. Perfect. Oh, this is another thing I wanted to see, my speed when we actually enter the sphere of influence of the moon. It's probably going to be pretty different because, as you can see, we're entering the sphere of influence well before we actually reach our apoapsis. And we're at 440, so not great, but in the region, I guess. Oh, duh, the thrust limiter's on. Okay, yeah, that looks like a much more reasonable burn time. And we're in orbit, and the tank is almost completely drained. This is spot on. I think this might legitimately be the lightest craft that could ever do this specific mission. Okay, we had a little bit of fuel, so I'm going to crash into the surface of the moon, but during that, I'm going to sign off. So I think I'm going to make another video where we redo this math for the real moon and see if we could get something interesting there. You have to keep an eye out for that. I also might do some more KSP videos with more over-engineering, depending how this one actually turns out once I'm done with it. But for now, I'm Hathy, and I will see you in the next video.